G'day viewers, in this episode we are going to present two methods, that is options, relating mass, charge and spin angular momentum to the quantum vacuum. We'll circle back to what these methods are shortly, but for now we recommend all viewers to watch episodes 90, 93, 94 and 95 if you have not already done so prior to continuing. By assisting us in this way, we do not need to repeat fundamental concepts and consequently we can minimise the length of this video presentation. Moreover, this enables us to tie episodes 93, 94 and 95 and this one together. Your assistance is greatly appreciated. In episodes 93 and 94, we calculated the spin energy required to power the phenomenon of spin angular momentum from the dark reservoir of quantum potential energy via the zero-point field interface. In order to execute these calculations, we required knowledge of particulate mass moment of inertia. Consequently, we assumed a classical representation of particles, that is, each particle is treated as a spinning ball. The problem this introduces is that particles are not actually spinning balls, and the classical representation of particulate matter is, at best, a useful approximation only. So then, what does this mean? Well, it means that we need to ask the following question. Do we actually need to estimate the spin energy? If the answer to this question is yes, then we should utilise method 1, that is option 1, whereby the spin frequency calculation is kept isolated from the spectral convergence frequency associated with mass and charge. Moreover, by keeping the spin frequency isolated from our quantum vacuum harmonic cutoff frequency calculation, we retain enough flexibility in order to recompute spin energy calculations based upon alternate mass moment of inertia configurations. However, if the answer to our question is no, that is, we do not need to estimate the particle spin energy, then method 2, that is option 2, becomes the preferred solution because mass, charge and spin angular momentum are unified with respect to the quantum vacuum. Having said this, method 1, that is option 1, may still be utilised if we wish to isolate the phenomenon of spin angular momentum from the quantum vacuum for whatever reason or motivation we have for taking this approach. So pretty much the choice between option 1 and option 2 becomes a matter of personal preference, depending upon whatever our particular research objective or modelling requirements might be at the time. Okay, let's get into the quantum vacuum spectral convergence derivation process of mass, charge and spin angular momentum. We will begin with the first 4 steps defined in episode 90 and 94. Step 1 recognises that the time required to travel a distance of 2 pi r is equal to the time it takes to sweep through 2 pi radians, yielding omega sub theta as shown. Step 2 introduces the standard expression for spin angular momentum. Step 3 defines the energy density associated with spin angular momentum. Step 4 defines the spectral energy density associated with the quantum vacuum if and only if the quantum vacuum is dynamically, kinematically and geometrically similar to the rotational frequency associated with omega sub theta as appears in step 1. I will also take a moment to emphasise that we have executed a quality assurance check appearing on the right hand side of the slide. The purpose of this was to ensure that steps 3 and 4 produced the correct dimensional units. Viewers may disregard the actual numerical results. They are not required going forward. In the lower half of the slide, you see a generalised depiction of particulate matter. This is an excerpt from episode 93, which visually communicates spin radius, zero-point field equilibrium radius, the dark reservoir of quantum potential energy, and the origin of spin angular momentum. We will explore these concepts more on the next slide, which is also taken from episode 93. Okay, let's now look at what particle radii, that is, particle size, physically means. The question we are going to investigate now is, what is particle size? That is, what exactly is particle radii? Whilst the concept of size may seem very straightforward to most people, particle physicists would disagree because particles do not have a solid boundary. Thus, the concept of size is somewhat ambiguous and open to interpretation. However, what we are going to achieve in this frame is a definition for 3 concepts of size, all of which are equally valid and applicable. We shall define spin radius, zero-point field equilibrium radius, and classical charge radius. Firstly, we shall define spin radius as the physical dimension which powers spin angular momentum via the dark reservoir of quantum potential energy. In other words, energy flows from the dark reservoir of quantum potential energy to a particle which powers the spin phenomenon in perpetuity. Please remember that, from the perspective of physics, particle spin appears to be a case of perpetual motion. However, the issue with perpetual motion is that it violates the laws of thermodynamics. Thus, our explanation of energy exchange involving the dark reservoir of quantum potential energy preserves the laws of thermodynamics. We will circle back to the concept of the dark reservoir of quantum potential energy shortly. Next, we shall define the zero-point field equilibrium radius as the physical dimension that the quantum vacuum perceives a particle to be. For example, proton, neutron and electron. Please remember that our zero-point field equilibrium radius concept has been experimentally verified for the proton and neutron. Please refer to episode 5 for more information. Lastly, we shall define the classical charge radius as the physical dimension, that is, the size, that one charged particle perceives another charged particle to be. In other words, it is the physical dimension which characterizes particle interactions at the atomic scale, for example, the classical electron radius. As promised earlier, we will now discuss the dark reservoir of quantum potential energy in a bit more detail. To begin with, let's ask the question, what is energy? Simply put, energy is defined as the ability to do work. Hence, potential energy becomes the potential to do work. Thus, quantum potential energy may be defined as the potential ability to do quantized work. Okay, so now we have defined quantum potential energy. What about the dark reservoir? When we speak of the dark reservoir, we are referring to the existence of a conjectured fourth spatial dimension, or in other words, we are referring to the existence of a conjectured fifth space-time dimension. That is, if you prefer to think in terms of general relativity. Either way is fine. Since the dark reservoir comprises of quantum potential energy only, it has no inherent structure associated with the potential energy it contains. This is not unusual, of course, as no form of potential energy can have any structure associated with itself because by definition it has not done any work yet. It only has the potential to do work. Potential energy does not attribute structure to any form of energy until it is released. The dark reservoir of quantum potential energy has the potential to release quantized energy, so it cannot possess any experimentally observable inherent structure, as previously discussed. However, having said this, because its energetic structure is, figuratively speaking, undefined, it is entirely reasonable to assign an energetic structure to the dark reservoir of quantum potential energy if it assists in solving a related challenge. Assigning energetic structure to the dark reservoir of quantum potential energy is analogous to assigning a datum when appropriate, which is common practice across multiple engineering disciplines. In other words, because the dark reservoir of quantum potential energy has no inherent energetic structure, we are free to theorize in any manner we wish if it serves our purposes to do so. On the next slide, we will revisit the mass and charge spectral convergence derivation process we executed in episode 95. We shall do this so that we do not need to describe the spin, mass and charge spectral convergence derivation process from scratch later in the video presentation. That is, we will only need to communicate key events. Okay, let's revisit episode 95. The spectral convergence derivation process commences with the selection of a physical model to analyse. Herein we shall utilise two similar fundamental charges, hence they are repulsive. However, the results we will present on the next slide are unaffected by the choice of similar or dissimilar fundamental charges. Thus, utilising equally attractive or repulsive fundamental charges does not alter the outcome. Okay, let's now walk through the spectral convergence derivation process step by step. Step 1 derives the electrostatic spectral energy density. In episode 34, we derived a relationship between the electrostatic force and the quantum vacuum. We did this in order to solve the long-standing and well-known many orders of magnitude problem. We showed that a 90-degree phase difference exists between the quantum vacuum, electrostatic and gravitational spectra. We recommend all viewers to review episode 34 before continuing. Step 2 involves two parts. The first part derives the electrostatic force density. The second part relates the electrostatic force to Newtonian acceleration via Buckingham pi theory. Please review episode 1 before continuing. Step 3 converts the resultant quantum vacuum acceleration arising from electrostatic and gravitational forces into a cubic frequency distribution utilizing Buckingham pi theory. Step 4 quantizes the output from Step 3 into quantum vacuum spectral frequency form whilst obeying Fourier harmonics. Step 5 defines the ratio of energy densities for utilisation in the harmonic cutoff function. Okay, now that we have revisited the mass and charge spectral convergence derivation process from episode 95, let's look at the spin, mass and charge spectral convergence derivation process. By revisiting the derivation process from previous episodes, we have saved ourselves a bit of time on this slide. That is, we can jump into the key events without delay. These events occurred at Step 1 and Step 3, that is, where centripetal acceleration has been injected in Step 1 and its contribution incorporated into the ratio of energy densities appearing in Step 3. However, the resultant quantum vacuum acceleration appearing in Step 1 does have some special qualities. The special qualities exhibited by the resultant quantum vacuum acceleration appear on screen. We can see from episode 95 that the direction of the gravitational acceleration vector has no discernible computational impact upon the cubic frequency distribution associated with the quantum vacuum. However, the same cannot be said for the inclusion of the centripetal acceleration vector. We determined that a minor computational impact exists upon the cubic frequency distribution associated with the quantum vacuum, and we shall explore this on the next slide. Firstly, please note that the Higgs boson is a special case because it possesses zero spin angular momentum and zero charge, which is why it appears where it does in the table. So we will basically exclude it from the conversation for now. We shall begin by walking through Table 1, as appears on screen. Table 1 contains 8 columns. The columns of most interest to us are Column 2, Column 3, Column 6 and Column 7. The remaining columns are self-explanatory, particularly if you notice the nomenclature tile in the top right-hand corner of the slide. Columns 2 and 6 display the harmonic cutoff frequency when the centripetal acceleration vector is negative, whereas columns 3 and 7 display the harmonic cutoff frequency when the centripetal acceleration vector is positive. We show that, for charged particles, the similarity between solutions is extremely high, so any impact upon the solution derived in this episode is trivial. For neutrally charged particles, the similarity between solutions experiences minor impact, that is, a dissimilarity of approximately 30%. We describe it as minor because the harmonic cutoff frequency is many orders of magnitude above the Planck frequency. Hence, being so far above the Planck frequency means that a 30% disparity isn't that meaningful. Okay, let's move on to our next table of results. In Table 2, we lay out the solution algorithm in numerical terms via 10 columns of information. Columns 2 and 7 denote the spectral convergence factor, columns 3 and 8 denote the harmonic cutoff mode, columns 4 and 9 denote the spectral convergence radius, and columns 5 and 10 denote the harmonic cutoff frequency. The spectral convergence radius specifies the physical dimension whereby mass, charge and spin angular momentum are unified with respect to the quantum vacuum. The harmonic cutoff frequency specifies the quantum vacuum upper spectral frequency limit, specifically at the spectral convergence radius. In other words, the spectral convergence radius and the harmonic cutoff frequency go hand in hand. The spectral convergence factor is a numerical guesstimate required to initiate the execution of the solution algorithm. This is a common technique utilised in the information technology space, so it should be familiar to many viewers. The reason it is termed the spectral convergence factor is because the quantum vacuum converges to a single harmonic mode, which can be seen by the results displayed in columns 3 and 8. The results displayed in columns 4 and 9 and columns 5 and 10 denote the solutions satisfying the condition of unity displayed in columns 3 and 8. In other words, once columns 3 and 8 have been generated, the solutions in columns 4, 5, 9 and 10 simply drop out because they satisfy the constraints defined by columns 3 and 8. In Table 3, we execute a side-by-side scale comparison. Firstly, we look at the spin radius as appears in column 2. This is the physical dimension which powers spin angular momentum from the dark reservoir of quantum potential energy via the zero-point field interface. Secondly, we look at the spectral convergence radius pertaining to mass and charge as appears in column 3. This specific configuration of spectral convergence radius denotes the physical dimension whereby the quantum vacuum electrostatic spectrum converges with the quantum vacuum gravitational spectrum. The concept of spectral convergence means that both spectra, that is mass and charge, share a common harmonic frequency mode. That is, the harmonic cutoff mode equals unity. This means that both spectra may be described by a single harmonic frequency mode termed the quantum vacuum upper spectral frequency limit. Thirdly, we look at the spectral convergence radius pertaining to mass, charge and spin angular momentum as appears in column 4. To cut a long story short, the same principle applies to this configuration involving spin angular momentum as we just described in relation to mass and charge appearing in column 3. Lastly, we look at the zero-point field equilibrium radius as appears in column 5. It is important to recognise that the principle of zero-point field equilibrium radius has been experimentally verified against all presently available confirmed particle size measurements. It may be surprising for viewers to learn that the physical size of so few particles have been experimentally measured and confirmed. Of the 17 particles listed in column 5, only 2 of them have been experimentally measured to high precision. That's less than 12% of the column 5 population. I would like to draw your attention to the purple numbers appearing in columns 2 and 4. The purpose for this emphasis is to accentuate the fact that the spin radius, which represents mechanical rotation, generates results within 2 orders of magnitude of the spectral convergence radius associated with mass, charge and spin angular momentum with respect to neutrally charged particles, with the obvious exception of the Higgs boson, which is a special case particle. The reason this alignment of results is significant is because the methods and physical principles utilised to generate the results appearing in columns 2 and 4 are vastly different. The fact that the results associated with 6 particles align so well when they have been derived utilising vastly different methods and physical principles is noteworthy. These 6 particles represent greater than 35% of the particle population appearing in columns 2 and 4. In Table 4, we execute a side-by-side frequency comparison. The spin frequency as appears in column 2 denotes the mechanical rotation frequency of each particle. Column 3 specifies the quantum vacuum harmonic cutoff frequency associated with mass and charge. Column 4 specifies the quantum vacuum harmonic cutoff frequency associated with mass, charge and spin angular momentum. Once again, I would like to draw your attention to the purple numbers appearing in columns 2 and 4. The spin frequency, which represents mechanical rotation, generates results within 2 orders of magnitude of column 4 results with respect to neutrally charged particles, with the obvious exception of the Higgs boson, which is a special case particle. We have also emphasised the numerical magnitude of the results between columns 3 and 4 pertaining to charged particles. We can see that the quantum vacuum harmonic cutoff frequency associated with column 3 generates results within 2 orders of magnitude of column 4 results. Okay, let's now analyse what we have derived so far. The first thing we will do is take a closer look at the orders of magnitude relationships we just mentioned. We can see that the relationship between columns 2 and 4 on Table 5 is 2 orders of magnitude, as expected. Moreover, the relationship between columns 7 and 8 on Table 6 is also 2 orders of magnitude, once again as expected. From these orders of magnitude relationships, we can see that the ratio between them is approximately 2.4. This implies that our spectral convergence solution, which incorporates spin angular momentum, is seemingly consistent across the entire population of neutrally charged particles and charged particles. So what does this mean? Well, it means that we have 2 options available to us. Number 1, we can treat spin angular momentum as a discrete and disconnected physical phenomenon from the quantum vacuum spectral convergence we have demonstrated incorporating mass and charge. In other words, columns 2 and 6 stand alone from columns 3 and 7. However, the contribution of columns 2, 3, 6 and 7 combined represent a complete solution describing particulate mass, charge and spin angular momentum. Or, number 2, we can consider mass, charge and spin angular momentum to be unified physical phenomena via the quantum vacuum. Consequently, columns 4 and 8 represent a complete solution describing particulate mass, charge and spin angular momentum. So then, which option should we use going forward? Well, to answer this question, we need to reflect upon a few things. In episodes 93 and 94, we calculated the spin energy required to power the phenomenon of spin angular momentum from the dark reservoir of quantum potential energy via the zero-point field interface. In order to execute these calculations, we required knowledge of particulate mass moment of inertia. Consequently, we assumed a classical representation of particles, that is, each particle is treated as a spinning ball. The problem this introduces is that particles are not actually spinning balls, and the classical representation of particulate matter is, at best, a useful approximation only. So then, what does this mean? Well, it means that we need to ask the following question. Do we actually need to estimate the spin energy? If the answer to this question is yes, then we should utilise option 1, whereby the spin frequency calculation is kept isolated from the spectral convergence frequency associated with mass and charge, as appears in column 3. Moreover, by keeping the spin frequency isolated from our quantum vacuum harmonic cutoff frequency calculation, we retain enough flexibility in order to recompute spin energy calculations based upon alternate mass moment of inertia configurations. However, if the answer to this question is no, that is, we do not need to estimate particulate spin energy, then option 2 becomes the preferred solution because mass, charge and spin angular momentum are unified with respect to the quantum vacuum. Having said this, option 1 may still be utilised if we wish to isolate the phenomenon of spin angular momentum from the quantum vacuum for whatever reason or motivation we have for taking this approach. So pretty much the choice between option 1 and option 2 becomes a matter of personal preference, depending upon whatever our particular research objective or modelling requirements might be at the time. For interested viewers, you can find a list of useful references on the next slide.